Okay. Dear students, up to now we have seen two forms of mathematical induction. Let's recall them. So, the principle of mathematical induction says that for each unary predicate phi over natural numbers, if phi holds for 0 and for each natural number n, let it be n, the variable, for each natural number n, phi of n implies phi of n plus 1. If these two are true, then every natural number satisfies phi. And another statement we have called a form of mathematical induction was the least number principle. It says that for each property, if there exists some number that satisfies it, then there exists the least number with that property, so that phi of m holds, but for no lesser number, lesser than m, that is, phi holds. So there exists m, which is the least, minimal m, that is such that phi of m holds. There is the least property. There is the least number with property phi. Of course, that's not that obvious that L and P is indeed logically equivalent to mathematical induction, but we shall prove it. But first of all, we shall consider another form of mathematical induction. I'll call it SIP. That is the strong induction principle. What does it mean, and why is it so strong? This principle is quite interesting. In general, it says something like that. If some property holds for 0 and so on, if the fact that, okay, let's be more accurate. If for each n, from the fact that our property holds for every number less than n, if that's enough for phi to hold for n, then phi holds for every natural number. If you wish, you may add the condition phi of 0 here, but strictly speaking, it is not necessary here. We shall see why. So, strong induction means that now it is allowed to infer phi of n plus 1 not only from phi for n, but from phi for all lesser numbers. So now this is, of course, superficially, it is stronger than MIP. Why? because here we are allowed to use weaker precondition. This implication is weaker than this one. So if it follows from n, then most surely it follows from phi for all lesser numbers. But I realize that it doesn't sound too clear. So let's do it in more systemic way. Where? Here. Of course, thank you. That's phi of n. Or otherwise, this quantifier wouldn't make much sense. So no lesser number satisfies phi thing count. Okay. First of all, let's do some abstract work. We say that a property phi of n is progressive. If and only if for each n, if this property holds for every number less than n, then it holds for n. Of course, this arrow is exactly the same as this one. So what does it mean? A property is progressive if and only if it is enough for phi of n that phi holds for every lesser number. By the way, can you name at least one progressive property? We'll write prog of phi if phi is progressive. Consider, for example, the following property. N is even. Is it progressive? Is this property progressive or not? Why? That's quite clear. Is it the case that every natural number less than 1 is even? Is it true or not? Which naturals are less than 1? 0. Is 0 even? Of course, 0 equals 2 multiplied by 0, it's even. So, that's true. But according to the progressiveness property, it should be that even or 1. Is it true? Is 1 even? No, 1 is not 7. So I see that if I substitute 1 for n here, this implication wouldn't be true. So that means that even, it's not progressive. We see a situation when all numbers up to n are even, yet n itself is not even. Interesting. Is property odd is progressive? Odd of n, that is, not even. Is it progressive? Really? No, it isn't. Let's substitute 0 for n. For each m less than even, m is odd. Is it true or false? Every natural number that is less than 0 is odd. Oh, gentlemen, what do you think? Is this property true or false? Why? Can you give an example of a natural number less than 0 that is not odd? No such example. Do you remember all that stuff about the present king of France? So we know he is bald. But likewise, he is hairy. How is it possible? Exactly because of the fact that there is no present king of France. There are no naturals less than 0. So what does it mean? That means that for each natural number m, you know, our quantifiers are over naturals. For each natural number less than 0, that means that for each natural number, if it is less than 0, then it is odd. But this is false. No naturals are less than 0. From falsity it follows everything. From falsity it follows everything, so this implication is true. All this thing is true. This whole thing is true. Yet, of course, it is not the case that 0 is odd. 0 is even. So, the assumption is true, yet the conclusion is false. That means that our implication fails. So, no, odd is neither progressive. No, it's not progressive. Property, the property to be even is not progressive. The property to be odd is not progressive. Interesting. What else? Say, what if we consider the following property, something trivial? I don't know, n equals n. You know, every natural number equals itself. Let's denote this property somehow. Ec of n. Is this property progressive? Most surely. Progressiveness means what? That given some assumption, every natural number satisfies our property. But for whatever assumption, this is true. Every natural number equals itself. So this whole implication is true, so it is progressive. That's progressive. It is progressive, and every natural number satisfies this property. But can you please give a property that not every natural number satisfies? There is a natural without that property, but that property is progressive. Is it possible? In fact, it's not possible. Why? At first, let's obtain some intuition about this thing. You know, progressiveness means that if your property has taken all numbers less than n, then it also takes n. But what does it mean? That means that now it owns all numbers less than n plus 1. Applying this statement, you may conclude that it also takes n plus 1. Now, it has taken all numbers less than n plus 2. According to this statement, it takes n plus 2 as well, and so on. So if it is progressive, every natural number satisfies that property. Is it clear? But, of course, it is intuitively it is quite clear, but we can't prove it in any other way than induction. So, in fact, this statement that every progressive property takes all natural numbers, this fact is called the strong induction principle. It's called the strong induction principle. So, for each phi, if phi is progressive, then every natural satisfies phi. Is it clear? Oh, by the way, this thing is quite close to our inductive step. In this case, the inductive step says that if phi takes n, then it takes n plus 1 as well. But no, the inductive step is trickier. Now we say that if phi takes all numbers less than n, not only the previous one, but every number less than n, then it takes n. But in this case, we need the base, phi of 0. But where is the base here? Supposedly, there is no base. It's not good for induction. But in fact, there is a base. Let's prove it. For it is quite interesting. Okay, I say that if phi is progressive, then 0 necessarily satisfies phi. The proof is very easy. What does it mean that phi is progressive? And that's given. It's the assumption. Assume that phi is indeed progressive. That is, for each n, if every lesser number satisfies phi, then phi of n also holds. This is given. And that's true for every natural number n, for every, including 0. Let's take 0 as n. It should be the following implication. For each m which is less than 0, this implies phi of 0. Ha! But equivalently, it says that for each m, if m is less than 0, then phi of m. And this statement implies phi of 0. Okay, this is false. Is it? No naturals less than 0. For every natural, that's false. It's not possible for a natural number to be less than 0. From falsity, it follows everything. So this assumption is true. It's true. And the whole implication is true. Why? Because it's given. Our given implication is assumed to be true. Its assumption is true. Hence, under our assumption, this conclusion must be true. Then phi of 0 must be true. So, is it clear? It's abstract, of course. What does it mean that it is abstract? That means that our property phi is whatever you wish. We don't fix it to be evenness, oddness, or something concrete, something easily imaginable. Oh, that's some phi, some property, whatever. So this is our principle. And now, let's use it and prove something quite concrete, not abstract. Concrete means not abstract, not made from concrete. I know, like that wall. Not this one, but that one. Okay. Let's prove the following statement. That's just ST for statement. Let R, or beta A, be a real number. Do you know what a real number is? At least intuitively. Numbers like, I don't know, pi, e, square root of 2, every rational number, and so on. Let A be a real number such that A plus 1 over A is integer. This number is integer. Do you know any examples of such numbers? If A is 1. Anything else? Only one example? I doubt it. In general, is it possible that this number, say, equals 3? Of course, a is not 0, so we may multiply both parts by a and obtain something like that. Which is just a squared minus 3a plus 1. Okay. It's an equation of degree 2. Does it have any real root? Yes. Why? Because if we consider the discriminant, it would be what? 9 minus 4. It is 5. It's greater than 0. So it has two distinct real roots. There are such numbers, infinitely many of them, in fact. Okay. But that doesn't matter for our statement. Let a be a real number such that a plus 1 over a is integer. Not necessarily 3, but some integer. Then I say, for each natural number n, a to the power n plus 1 over a to the power n is integer as well. So for every such number, if you replace it by its nth power, the result will still be integer. How is it possible to prove it? Of course, by induction. For here we have a quantifier over naturals. We want to prove something for each n. And now, in order to see which form of induction is most applicable here, most nice to use, let's solve it essentially, so intuitively, without any unnecessary formalism. So let's take some naturals. What if n equals 0? Then let's consider some cases. A to the power 0 over a to the power 0 is what? Why? Because this is just 1. So that's 2, which is integer. What if n equals 1? This is the number from our assumption. It is integer y by the assumption. By the assumption. Ha! And now the tricky part. N equals, say, 2. Why this number is integer? Gentlemen, do you have any idea? So? So you won't take a square of what? Of this one. Okay, let's try it. Is a squared plus this one plus 2. So this number is integer, of course. This is integer as well. 2 is integer. So the difference of two integers is integer. Okay. What about 3? What about 3? Don't you want to consider the cube? No. So you wish to multiply these two. They are integers. Okay, let's try. A cubed plus 1 over a cubed. That's nice. What else? What else? 1 over a. So and also a. Ha! So if we denote our number somehow, say s n's, then we see that s2 multiplied by s1 equals s3 plus s1. Or likewise, s3 equals s2 multiplied by s1 minus s1. Of course, if these two are integers, the product of two integers is integer. The difference of two integers is integer. So this is integer. Okay. And what about 4? Can we generalize this idea? Can we generalize it? Can we express this number in terms of one or more previous ones? So how? What should we do? Probably we have to multiply this one by this number in order to get a to the power 4. What is it? A4 to the power 4, of course. This one. What else? If we multiply these two, we will get a 1 over a squared. And if we multiply this one and this one, interesting. We see that S4 equals S3 multiplied by S1 plus S2. Excuse me. Y plus So, of course, minus. So we see that this is a. This is our number. So anyway, that's quite clear. Our number equals this product minus S2. So we see something like that. If S2 and S3 are integer, then S4 is integer as well. This clearly suggests some induction. By the way, is this statement true in general? Let's state it generally. If S and S are integer, then S is integer as well. 2, 3, 4. And in general, if the list is, no, not the list, but the first number is Sn, then S n plus 1, and here n plus 2. Is the statement true or false? Okay, let's prove it. So first of all, we consider this product following our model, our previous examples. Which is a to the power n plus 1 plus a over a to the power n plus 1 plus what? No, it's not good. So here we have 1 over a to the power n and a to the power n. So this is S n plus 2 plus Sn. Of course, it's not n, but 1. Thank you. So, in general, I see that Sn plus 2 equals Sn plus 1 multiplied by Sn minus Sn. So that means that if these two are integer, then Sn plus 2 is also integer. So, this is integer depending on two previous numbers being integer. So we are doing 2 steps behind. 2. Not 1, like here, but 2. That means that we apply the strong induction, in order to check that this one is integer, we need that two previous numbers in our sequence are integers. Is it clear? So, now let's do it formally. Let's do it formally. This holds for every natural n, by the way. So my phi of n is just the following property. This number is integer. I want to prove that it is progressive. Let's do the same thing, but now formally. I say that it is progressive. In order to prove progressiveness, I have to assume that so I want to prove this implication under a universal quantifier. Let's consider some arbitrary natural n and assume that for every less number, phi of m indeed holds. And I need phi of n. So I am given that this is integer, and I want that this one is integer as well. So this is some n. But I know that integrity, that is the property of being integer, integrity of Sn and n plus 1 is enough for integrity of n plus 2. But n here must be natural. What if you consider two base cases, 0 and 1? Can you express 0 in this form for a natural? Of course not. Of course not. So two first numbers, you should consider them separately. So I need this one. First case, n equals 0. In fact, we have already considered it. So we know that this is true. So everything is okay in this case. The second case, n equals 1. Likewise, everything is okay. The third case, n is at least 2. But then n equals some m plus 2, where m is a natural number. Clearly, m is less than n, and m plus 1 is less than n. Is it clear that m is less than m plus 2? Ha! But by this statement, which could be naturally called the inductive hypothesis, by the inductive hypothesis, every lesser number satisfies our property. So m and m plus 1 are less than n. So they do satisfy. By the inductive hypothesis, using this fact, this assumption, I can say that this number is integer and this one is integer as well. Or using our notation, where this was called Sn, using our notation, I see that m and m plus 1 are both integers. But I have already proved this thing. Let's mark it with a star. That if Sm and Sm plus 1 are integers, then Sm plus 2 is integer as well. By my star marked statement, I may conclude that this number is integer as well. So that means that Sn, n you know is m plus 2, is integer. And this is exactly the statement I need. Is it clear? Here, the application of strong induction principle is not, I'd say, full-blooded. Why? Because we are doing just 2 steps behind. From every number to the previous one and to the previous. But in general, there are many cases, many statements, when you need your statement to be true for every lesser number. We shall see such examples at this seminar. And now I want to do something even more abstract. Anyway, gentlemen, that's mathematics. Sometimes you need an abstract general theorem. Which theorem I want to prove? Which one? In fact, I'll prove that all these 3 principles are pairwise equivalent. That means that each of them can play a role of the axiom of induction. And the other 2 are logically equivalent to it. It is not hard, but a little bit tricky. We'll go slowly. Okay. Our first serious theorem says that the following statements are pairwise equivalent. What does it mean pairwise? That is, every two of them are equivalent. First, strong induction principle. Second, the least number principle. Third, the principle of mathematical induction. Of course, formally we, not formally, but naively. Naively, of course, we have to consider every pair of our principles at the first glance. But that's not needed. In order to prove that three statements are pairwise equivalent, it is enough to prove three implications, from 1 to 2, from 2 to 3, and from 3 to 1. Is it clear that if we have proved these three implications, we will prove the equivalence of every two principles? Is it clear? Why, for example, from 2 follows 1? Because from 2 follows 3 and from 3 follows 1. And implication is transitive, that is, if from A follows B and from B follows C, then from A follows C. So, I want to prove three implications. Let's start with the first one. I'll use this part of the blackboard. What is assumed? Our strong induction principle is assumed. That is, for every phi, if phi is progressive, then every natural number satisfies phi. By the way, what if I rename phi to some other letter? Would it break anything? No, of course. Let's rename it to psi. Like in psychology, psi. Okay. That's given. It is assumed. What is needed? I need to prove the least number principle. That is what? For each phi, if there exists some n with property phi, then there exists some m, so that phi of m, but for every lesser number, phi does not hold. Of course, not implication, but conjunction. Here we have a conjunction. Is it clear? Not implication, but we excuse me. Oh, of course. Excuse me. That's implication. If there is a number with property phi, then there is the least such number. Thank you. All right. Okay. Let's prove it. The main idea here is as follows. We want to apply SIP not to phi, but to the negation of phi. So, in order to prove it, we may assume the following. So, we may assume that indeed, there exists some number with property phi. And we want to prove that there is such number. Okay. Let's try it. How is it possible to prove something? It's possible to go from the contrary. Assume that this doesn't hold. So, what does it mean that this doesn't hold? Let's construct a negation to this statement. This says that there is a natural number satisfying phi, so that no less a number satisfies phi. What is the negation? There exists m such and such. What is the negation? No m satisfies this property. So, for every m, this is false. What does it mean? For every m, this conjunction is false. That means that for every m, either this is false or this one is false. Do you agree? Why is it so? Let's recall some logical equivalences. When a conjunction is false, a conjunction is false if and then if either of its members is false. And another interesting step. Not C or D is equivalent to when an implication is true, when its assumption is false or the conclusion is true. So this is equivalent to what? C implies D. Do you agree? And what if we take this one as D and this one as not C? That means that this is equivalent to the following. For each m, if C holds, then not phi of m. Is it clear? That's very close to what? What does it mean that some property f is progressive? That means that for each x, if for every y less than x, f holds, then f holds for x. Ha! Clearly, this is a progressiveness statement. The progressiveness statement for some property. For which one? What plays the role of f? Compare these two. The negation of phi. Clearly. Ha! That means that not phi is progressive. If there is no least element with property phi, that means that not phi must be progressive. But I know that every progressive property claims all natural numbers. This is for every psi, including not phi. Not phi is still some property. Why not? So, by our strong induction principle, that means that every natural number satisfies not phi. But earlier we assumed that there is some natural with property phi. Let's mark it with sharp. Okay. By our earlier assumption, there exists some n with property phi. What does it mean? No natural satisfies phi, and some natural satisfies phi. What does it mean? This two means that we have got a contradiction. But this contradiction is quite a good thing. Why? Because we have earlier assumed that this does not hold. This means that our assumption, let's mark it by star, our assumption our star marked assumption fails. That is, in fact, there exists M so that phi of M, and for every lesser number, phi is not true. We have assumed that there is no least number. Then we transformed this assumption logically, and we have got exactly the progressiveness property for not phi. Using SIP, we concluded that no number satisfies phi, which contradicts our assumption that at least some number does satisfy. So we have got a contradiction when we assume that this is not True. Hence, it is true. Is it clear? Any questions, please? You may find the transcript of this proof in my lecture notes. It is abstract, but not too hard. Can we move further? Let's prove one more implication, and the last one will be postponed for the next lecture. Let's prove that, okay, now this is done. Let's prove that from the least number principle, it follows MIP. It follows our plain induction. Here we don't need SIP, so we may safely erase it. No, we need progressiveness. So another statement. From the second one, it follows the third one. What is assumed? The least number principle is assumed. That is, for each psi, let's rename, for each psi, if there is at least one number satisfying psi, then there is the least such number. Not psi of n. There is a number satisfying psi, but such that no less number satisfies psi. This is assumed. What do we need? In general, I need MIP. What's MIP? For each phi, if phi of 0 holds, and if phi of 0 holds, and our inductive step holds, then if these two hold, then this is the same arrow, just another way to draw it. Okay. Then every number satisfies phi. Dear students, here I want to prove an implication. What's the general technique of proving an implication? Assume that the assumption holds. So I can assume that these two hold. And then it will be necessary to prove that every n satisfies phi. So I can add these two statements to my assumptions. Let's mark them somehow. This one, the base. Okay, let it be 1, and this 2. So these are my assumptions. And what do I need? Now, I need that every natural satisfies phi. Is it clear? Okay. I want to prove that every natural satisfies phi. The main idea is as follows. I want to apply LNP to not phi. So I want to prove that not phi has no least element. That would mean that there is no element with property not phi, hence every number satisfies phi. Okay. Let's do it the following way so that we may obtain a contradiction. From the contrary, assume that it is not the case that assume that this is false. Assume that this is false. That is, what does it mean that not every n satisfies phi? That means that there exists n which satisfies not phi. Is it clear? And now let's apply our LNP to psi being equal to phi. Let's apply LNP to being equal to not phi. Let's apply LNP to not phi. So we know that there exists some n satisfying not phi. What does it mean by LNP? That means that this should be true for not phi. There exists m so that it doesn't satisfy phi, but every less number satisfies not phi. But what does it mean not phi? That's phi. Ha! Now we have got such a conclusion. Now let's analyze which number this m could be. Do you agree that every natural number is either 0 or some lesser number plus 1? So we have exactly two cases. First case, this m equals 0. Then clearly not phi of 0. If this m is 0, then not phi of 0. Ha! But we have assumed that 0 satisfies phi. By the assumption 1, we have phi of 0. These two bring us to a contradiction. Is it clear? My mind is free from these things. I am proceeding mechanically using logical transformations, and the only guiding idea that I need to apply MIP to not phi. So, what if m equals n plus 1? Is it possible? In general, why not? So we have not phi of n plus 1, but for every number which is less than n plus 1, then m, it should be phi. By the way, dear students, what do you think? Is n less than n plus 1? It is most true. As William Shakespeare would say. Okay. That means that phi of n holds. Phi of n holds. Phi of n plus 1 does not. Ha! But we have assumed that phi of n plus 1 follows from phi of n. So, using our assumption number 2, we obtain phi of n plus 1. And now, at this stage, we have both phi of n plus 1 and not phi of n plus 1, which is clearly contradictive. So, we have considered all possible cases and have got a contradiction. That means that our assumption that there exists such n is contradictive. So our assumption marked by star is false. If it is false, then this one is true. If there is no n that does not satisfy, then every n satisfies phi. So we have proved it. By the way, let's notice that in both cases we have switched from our property to its negation. But in this, in the remaining implication from 3 to 1, this trick won't work. We will need something else. Any questions, please? Dear students, all these things are abstract, but you are students of mathematics. Mathematics is abstract, formal science. So you should be ready for this kind of things. We are going slowly. We may come back to any point you have not understood. We may discuss it in our Telegram group. Please do not neglect. This is the place for discussions on our problems, our theorems. So thank you.